Right, today we are going to be integrating, using integration methods to work out the area of a circle. So we have a circle here with radius of 1. The centre to the outside the circle is 1, so the radius is 1. And the equation of this circle is x squared plus y squared equals r squared, where r equals 1. So x squared plus y squared equals 1. Equation of this circle. And to use the integration method, first we need to imagine that we're taking a strip, say like this, about the y-axis, coming off the y, and this will have a width of dy, sorry, a height of dy, and a width of x. So the dA, the area of this, equals x times dy. Imagine a strip like this. Dy here and then x here. So next thing we need to do is rearrange this in terms of x. So we have x squared equals y squared minus 1. So x equals square root of y squared minus 1 plus or minus. The plus here means that we're going to be integrating this portion to flow from here all the way to here, and then the minus would be on the other side of the y-axis. So now we have this, we're going to be integrating between 1 and minus 1, our boundary conditions, dA, which is x dy, which equals integrating this, which equals integrating sorry, 1 minus y squared, because I can't rearrange. 1 minus y squared. So I thought something's a little fishy. To the power of a half. So obviously the root means that we have this, the root can be written as power to a half. Right, times dy. So with respect to dy. Now, we're going to need to use substitution for this. So we say that y equals sine theta. So we can say that y squared equals sine squared theta. So we can say 1 minus y squared equals cos squared theta using this. So this comes from sine squared theta plus cos squared theta equals 1. Rearranging, we get to here. So here, now we've got this, and now we need to find dy. So we need to differentiate this term. So we get dy by d theta equals, what's the differential of sine theta? It is cos theta. So now we get that dy equals cos theta times d theta. So plug in this substitution into the integral, we get 1 minus 1 of 1 minus y squared cos squared theta to the power of a half times what's dy, cos theta d theta. So now, how are we going to do this? Well, we can straight away see that here, cos squared theta rooted would just be cos theta, times like cos theta would be cos squared theta d theta. Now, how do we get cos squared theta in a form that we can integrate? We need to use a power reduction formula. So we can say that we can use this term here that cos of A plus or minus B is equal to cos A cos B minus sine A sine B minus plus. So the opposite way round. And then we can say that cos of A plus minus A, or like 2A, equals cos squared A minus plus sine squared A. And then we can say that cos of 2A equals cos squared A. So now we've used plus, and now we have minus here. And then sine squared A, we said, can be rewritten as 1 minus cos squared A, which equals cos squared A minus 1 minus cos squared A is plus cos squared A. So now we have cos of 2A equals 2 cos squared A minus 1. And now we have a cos squared theta here and a cos squared A here, and we want to get the term that's in terms of without power so we can integrate it. So we need to rearrange in terms of cos 2A. So now we get that. Sorry, in terms of cos squared A, we want cos squared A on its own. So we get that cos 2A plus 1 equals 2 cos squared A. So now we get that cos squared A is equal to a half of this, because we're just dividing everything by 2, of cos 2A plus 1. So cos squared theta equals half cos 2 theta plus 1. So now we're basically integrating this of a half cos 2A plus 1. Sorry, 2 theta plus 1 with regards to theta. Now we can factorize the half, so half of this 1 minus 1 of cos 2 theta plus 1 times d theta equals a half. And then cos 2 theta integrated, cos theta goes to sine theta, and then we divide by the differential of the brackets. So sorry, if I draw the brackets then it might make more sense. So we get sine 2 theta over 2, then 1 integrated with regards to theta is just theta, between 1 and minus 1. So let's do some rubbing. We can rewrite this at the top. So if we have a half, sorry. So now we've got half sine 2 theta over 2 plus theta. But now we need to take a look at these boundary conditions, because obviously this integral where we use substitution is in terms of theta, but the boundaries are in terms of y. So because we use this substitution, y equals sine theta, we have y equals 1, we can say that y equals 1. So 1 equals sine theta. So theta equals inverse sine of 1, which equals pi over 2. And then if we were to use y equals minus 1 equals sine theta. So we get that theta equals minus pi over 2. So these are our new boundary conditions. So we can say that a half sine 2 theta over 2 plus theta. We're integrating not between 1 and minus 1, but between pi over 2 and minus pi over 2. So doing this, we can say that bring a half out, and we can say that, well, firstly we can see that sine of 2 times pi over 2, when these cancel out, it'll be, that's equal to sine pi. Sine pi in radians is 180 degrees in degrees, is equal to 0. So this term and minus pi over 2 will go to minus pi because we have to double it. So it also goes to 0. So this entire term goes to 0. So now really we're just doing half of theta between pi over 2 and minus pi over 2, which is the same as saying half of pi over 2, and then we get minus pi over 2. So this is what we're getting. So we get a half of pi over 2 minus pi over 2 is the same as pi over 2 plus pi over 2, which is just pi, which equals pi over 2 times it by half. So this is what we've got for a circle between 1 and minus 1. So this is technically pi times the radius squared, 1 squared over 2, which is pi r squared over 2, which you may be able to identify as the area of a semicircle. Why have we got the area of a semicircle? That's because we've used the positive square root at the start. If we were to integrate this negative, we'll get 2 times this, so 2 times pi r squared over 2 cancel, and we'll just be left with pi r squared, which we can all tell that is the area of a circle.